my name is Martin. I'm one of the founders of the Trino project. So today we're going to talk about the state of the project, talk about the community, how the community is doing. We're going to go over some of the recent improvements to the project and some of the things that happened over the past year. And then we're going to talk about the roadmap of what's going on in the community right now and what's going to happen, the projects that we're embarking on over the next few months. So if you're here, like I assume you know about Trino, you know what Trino is. There's a couple of things I wanted to clarify. So Trino, of course, is the new name of the Presto SQL project. We had to rename the project in December last year, but just to make it clear, it's the same set of people, it's the same software, the same community. We just have a new name, and of course that cute bunny that everyone loves right now. So we're gonna. One of the things I wanted to dispel is like this question of we keep hearing is like, well, why have two projects? Why is why are there two projects with the same code and different names? The reality is that the projects, since they split in 2019, they've evolved differently. They've evolved separately. They are vastly different projects now. In fact, I mean, you can see from this chart, this is a representation of all the commits in each of the projects over the past couple of years. And there's an interesting set of stats about this. So even though the project shared 6.5 years of history, 40% of all the changes in Trino, in the history of Trino, happened in the last 2.5 years. So, and all those features, all those changes are exclusive to Trino. Presto, of course, has its own changes, but they are completely different developments at this point. So, for all intents and purposes, like you think about them as two separate projects, just like I know Postgres and MySQL are different projects, right? And Trino is supported and has people from many companies involved, including companies like Starburst, of course, LinkedIn, Netflix, Verada, Salesforce, even Amazon's working on Trino. And it's used, the developers at those companies are actively investing in Trino and making it better. And those companies are also using Trino at scale in very, very large installations and for thousands of users. So some stats about what's been going on in the community over the past few months. We already have, in the history of Trino, more than 520 contributors. We are already up to 5,200 plus members in Slack, and we're adding about 200 members every month or so. And about 500 of those are active every week. I mean, people come and go, become active, less active, but that's kind of the number of people that engage in discussions, in conversations on Slack every single week. So far, we've done 13 releases this year. It's a bit lower number than we're used to. Historically, we've done releases every 2 weeks. This is about one every 3 weeks. Of course, releases this year have been bigger with bigger features, more development. But the cadence has slowed down. The pace has slowed down a little bit, and we're working on bringing that up to the usual 2 week releases or so. We're at about 400 commits every month, and that's it's actually an interesting number because it's. I was looking at some of the numbers over the history of Trino, and that's an increase in it's almost 50% increase since the project split. So. Since 2019, when Presto and Trino split up, activity in Trino has increased by almost 50%. So that's primarily due to more people getting involved, more people actually engaging in the project and contributing to the project. And of course, like after we renamed the project, we had a huge bump in visibility of the GitHub project. I think that's part of the reason for that is like having a different name has solved some of the issues around confusion with the two names.
And of course, the number of this is a chart that shows the number of stars on the GitHub repo. So we saw that bump, and since then the rate of stars has been increasing faster than before. And at this point, I think if you go and look at some of the other open source projects in the space, Trino is I think one of the fastest growing in terms of GitHub stars. So if you want to give us a GitHub star, there's a link there. Just click on it, and then just click on the star at the top right of the repo. So Trino currently is being used by thousands of companies all over the world and across every industry. And the number keeps growing. It's like we keep hearing about all sorts of random companies and people in different countries in the world that they just sign up for Slack and they start asking questions. So it's like, oh, it's surprising to see that many people and I mean, using and picking up Trino and using it and getting experience with it. If you are using Trino and you would like to get listed on the Trino users page, send us a note and we'll add your logo. And if you have a description of how you're using it, that would be helpful too. It helps other people understand how Trino can be used and how they can leverage the project. All right, let's talk about some of the recent changes, improvements. And just to recap, if you are curious about what happened in 2019 and 2020, we have 2 blog posts that summarize everything that happened in those years. We'll have one at the end of this year covering everything that happened so far. In April, around April, we had a meetup where we talked about some of the improvements in the beginning of the year. I'm not going to cover them, so you can just go to that link and you can see that for yourself. I'm going to talk about some of the things that happened since April till now. Lots of new features. This is just a short list of features, notable features. Keep in mind there's a lot more than this. So there are some language improvements. Notably, there's a feature called list tag in the SQL language that allows you to concatenate arrays and format them as strings. It makes it very easy to do that. So that was added a couple months ago. We added support for Parquet column indexes, which is a performance improvement feature if you're querying Parquet data. This was a feature developed by engineers at Uber and Lyft and Starburst. So it's still in experimental phase, but if you're using Parquet data, please go ahead and try it. And let us know if you see any improvements, any regressions. We expect this to help with a number of queries that take advantage of Parquet data. There are other features like more visibility. Connectors can now expose custom metrics. These can be collected and captured in the query completion events, so they can make it easier to see what's going on in connectors when if you're analyzing the events coming from a cluster. And there are a number of other improvements to connectors like Pinot. The Pinot connector can push down queries, aggregation queries into Pinot and take advantage of all the capabilities of Pinot to do efficient processing. We've supported Hive views natively in Trino for a while. We've been making some improvements to that feature, more compatibility with different shapes of queries and so on. And then on the security front, there have been a number of changes. Some of them to increase compatibility with different systems, like supporting opaque OIDC tokens allows integration with certain OIDC providers like the Google authentication system. We now support multiple authentication plugins, password authentication plugins. So if you're using LDAP or multiple LDAPs or Firebase and LDAP in a single cluster, you can combine them. And then there's a usability feature that makes it much, much easier to set up security in Trino clusters. Now you can have Trino workers and coordinators talking to each other via using TLS without having to deal with
certificate and provisioning certificates and so on. You just turn the feature on, and Trino takes care of setting everything up for you. So that's a massive improvement in the usability of the deployment and configuration. One of the more notable features that went in is this feature called match recognize, or actually row pattern recognition, that's defined in the SQL 2016 standard. It's a language feature that allows you to find patterns of in sequences of rows. This is one of those features that increases the power of the language. That there are many things you cannot simply cannot do in SQL unless you have this feature, or unless you can write your own like window functions or something like that. So the idea is you can, for example, let's take a quick look at this example. I'm not going to go into too many details. I don't want to bore you, but you can find more information in that link down there. But if you look at this specific query, there's that match recognize clause. There's a bunch of complex statements in there, but if you focus on the section that shows a pattern, this is a query that is trying to identify patterns in stock prices where the price goes down and then goes up, basically form a V. And you can define patterns based on expressions over the relationship of values across multiple rows. In this case, we define down. If you look at the bottom there, we define down as the price in a given row is less than the price in the previous row. And up is price in a given row is higher than the price in the previous row. And then the engine can combine those definitions into a pattern that, and then to be able to match that pattern you define. And then once it identifies those patterns, you can compute a number of values out of the rows that were matched. So this is super powerful feature. There are more examples on that blog post if you wanna follow and get more details. Also, row pattern recognition works in the context of window functions. So it's a generalization of window frames, where instead of just defining ranges for the rows that participate in a window frame, you can now identify individual rows based on patterns that you want to match. So this is super powerful, and again, you can find more in that blog post. All right, let's now talk a bit about roadmap. Just one point of caveat here. So roadmap in Trino has always been dynamic. It depends, it's subject to what contributors are working on, the companies that are involved in the project are working on, what they're prioritizing. So these are some of the projects that we've seen a few companies and developers deciding to invest in over the past couple months, and kind of going into the next few months and near future. So when we built Presto, or back in 2012 at Facebook, and then through the history of Trino, one of the biggest points of the biggest focus of the project has always been performance. And Trino is known for speed. It's known for efficiency. It's one of the has always been one of the most the fastest and most efficient engines out there. And this is something that we continuously look at, when we continuously invest in. So we're starting to look at a number of projects to take Trino to the next level in terms of performance. There are optimizations all over the place that we're doing on the different file formats, operators, etc. One of the areas where we're looking at making a big investment is the core evaluation engine in the system. So this is the idea, and we're sort of revamping that system to take advantage of what's commonly known as columnar evaluation. The idea here is you take expressions that you are going to evaluate, like filters and projections and so on, and break them up into sub-expressions that can be evaluated independently. And I mean, there are different techniques for how you split them up into those sub-expressions, but the benefit is that you can evaluate those sub-expressions over a smaller set of columns that have certain properties. Like, for example, if your columns are dictionary encoded or RLE is a form of encoding where if you have a number of repeated values, you just have the value represented once, and you just have a count associated with it. So there's a certain number of optimizations you can do when your system is aware of that type of organization. So by breaking up the expressions and evaluating them independently, the engine can take advantage of those features and do more efficient processing. For example, if you're applying a function to a value over an RLE column, you can do the computation once and then repeat the value n times, as opposed to doing it n times over each copy of the value. So that can speed up the processing orders of magnitude if you're smart about it. Doing this type of columnar processing also makes it possible to do a number of what we call adaptations, runtime adaptations to the data. For example, if you're performing a filter and with so you have an AND clause where you have expression A and expression B and expression C and so on, you can evaluate one of the AND clauses and then take advantage of what you found out about which rows are satisfy the first clause to filter out what other rows you're going to apply expressions on. So that allows you to save computation by not performing computations you actually need. It allows you to push down some of that knowledge about which rows are satisfy expressions into the connector, so the connectors can do more selective decoding of rows if they can take advantage of it. They could take advantage of indexes. They could take advantage of block encodings where you could skip across blocks and avoid decoding specific blocks if there's no rows that satisfy. And then, more importantly, it allows the engine to adapt to cost of executing expressions at runtime. For example, the engine may decide that evaluating a clause over a certain set of rows is more expensive because the function is more expensive, or the function is not, or the filter is not too selective, and it can decide to reorder the execution to evaluate the most selective filters that cost the least CPU first, and then perform the most expensive operations. And then the final thing is that by breaking up the evaluation into smaller expressions, it allows the engine to target some of the expression computations to sim the instructions in the CPU, or at a minimum make the code easier for the JVM to optimize and produce SIMD code, and then potentially use GPU for evaluating expressions in a parallel manner. We started doing some experiments over with this strategy of columnar evaluation and see what we can get, and we've seen a 4x improvement compared to the current performance of the evaluation loop. So it's very, very promising, and then this expands to a lot of other areas in the system that we can leverage. All right. So the next big and by the way, this is it's a project we're starting right now, and I expect more details to come over the next few months, and then it will expand into other areas of the system and will identify more opportunities. So the next big project we're starting to work on is to address a few challenges that people have when using Trino. So Trino is super fast. It achieves that speed because it's optimized for executing things quickly, but it does all the processing by streaming results in memory, pipelining executions, and so on. That imposes some trade-offs in terms of the kinds of things that you can and cannot do with when evaluating queries. One of the big limitations right now is that if you have a query that exceeds the amount of memory that you have available in a cluster, the query will fail, and it's like a cliff. Like the query may work fine until you exceed that limit, and then it stops working. And there's nothing you can do aside from adding more capacity. And in some cases, there are query shapes or data sets where even if you add more memory, you can't break go over that barrier because of skew and inability to parallelize the computation across more machines. So, which actually leads us to the second issue, which is if you have data that is skewed or computation that is skewed, your queries either they will fail and there's no way to get around that, or they will take longer to execute because you can't parallelize execution. When that happens, your query may be sensitive to failures in a cluster that can happen due to misconfiguration of the system. It can happen because, well, if you run a query that is 5 hours long or something like that, you may end up seeing failures in nodes. You may end up seeing failures due to other workloads interfering and so on. So this is kind of a usability challenge. It's one of the things that people have been asking for the system to improve. And we're starting to tackle that problem. And the way we're tackling it is by changing the core of the engine to be able to do retries of queries. So the idea is that you submit a query, you want the query to succeed no matter what. I mean, at some point, if the system is completely misconfigured, of course, like the query will fail and you'll have to deal with that. But we want obvious failures to be a non-event, or simple failures to be a non-event. And we're starting with, our strategies here is we're starting with the ability to do full query retries that are transparent to users. So this will benefit all the people doing interactive queries where there can be occasional failures. So if you submit a query and something fails, the system will be able to retry that transparently. You won't notice that there was a failure. Of course, you can go and look at after the fact that there were some failures and the system compensated for that. But that's good, but it's not sufficient because, like, if you have a big query, you don't want to retry the entire query when it's about to be done. That's a waste of computation. It's a waste of time. And if the query is long enough, you may never finish executing. You may keep retrying and every time encountering a failure. So we're going to go more granular than that, be able to retry individual stages in the query, and then eventually be able to retry individual tasks in the query. Once we get to the point of being able to retry tasks, and the set of things we have to build in the engine to be able to retry tasks gives us more flexibility in terms of how tasks get scheduled, how they get placed in different nodes as they need to compute. And it gives us more visibility into that process. And that opens up the door for more advanced features like auto-scaling support, where you might be running a query and the system decides, well, I have all these tasks I need to compute. I haven't started them yet. I have this pending queue of tasks. And you can, so the system managing Trino can observe that and allocate more machines, more resources, and let the system take advantage of them. So that's it's a super powerful mechanism to be able to adjust the size of your cluster to the demand of the computation in that cluster. And then, of course, this ability to see what needs to or have visibility into the queue of things that need to be run, have all these techniques for recovery where there have to be boundaries in the execution of the process of the query so that you can recover in a predictable manner, mean that the engine can see what's going on at those stages, and it can take advantage of information it gathers at those points to make better decisions about planning, about scheduling. For example, one of the things that it will be possible to do eventually is the query might start running. One of the stages may produce an intermediate result that the engine can introspect and get more statistics on, and you can use those statistics to plan or refine the next part of the plan. For example, you might decide to change the order of a join in the middle of the execution of a query compared to the decision they made in the beginning based on imperfect information from the stats in the table. And also these mechanisms of having, so being able to recover means we have to introduce points of spooling, which allow this type of planning I just mentioned, but it also means we can start using those pooling points as a way to reuse intermediate computations. For example, you may have a query that has a scan over the same table multiple times, if you're doing a self-join, for instance, or an n-way join between the same table. You can produce intermediate results with some filtering that is common to all the scans of that table, and then reuse those results in the subsequent parts of the query. So that's a potential improvement in performance. It's a reduction in I/O against the data sources and so on. And then, of course, it allows, this kind of fits right in with the way the engine performs execution of the with clause, which is effectively a way to reuse the same subquery across different parts across different branches in a single query. So with these mechanisms, we can optimize and execute with clauses more efficiently. And then the third project we're tackling, this is something that has been going on for a while. We've done incremental process over the past couple of years, and we're starting to get to the point where we have all the building blocks in place to be able to get it through the finish line. So the idea is, if you look at how functions are modeled in Trino, functions are static. Like, you have to define them upfront, you have to write the code upfront, compile it, and then deploy it in your cluster before the cluster starts. That is, I mean, it's good, but it's very limiting. It means that you can't change the library of functions after the fact without a restart of the cluster. You can have users define their own functions. And there's a bit of an asymmetry here, because you can do all that with tables. A user can go and create tables, you can drop tables, change them, you can add more data to tables and so on, but you can't do the same thing with functions. So that's kind of a very limiting feature. So what we're trying to do is get tables to behave in the same way that functions do. Functions in the same way tables do, where you can, in the same way you can create tables, drop tables, resolve tables dynamically, we want to be able to resolve functions at runtime as part of query analysis and evaluation. And on top of that, part of the goal is for plugins to be able to contribute functions to during query evaluation and functional resolution in a way that they don't collide with each other. I mean, the last thing we want is two plugins defining the same function with the same name, and then the system not be able to tell which one it should be using. So for that, we're introducing the concept of function namespaces. This is a concept that exists in the standard SQL specification. We're just implementing that part of the standard. So the idea is that plugins will be able to expose functions under catalogs and schemas, and you can, in a query, you can access the specific functions under a given catalog and schema, either implicitly by defining a lookup path, or by using the fully qualified name of the function. And we're very, very close to having that part of the system in place. Once that's in, we'll be able to start looking at the next set of features, which is it's actually the sweet spot of what we're trying to do, which is be able to let users define their own functions at runtime. Just like they can define their own tables, we want them to be able to define their own functions. And there are a few approaches here that we're going to take. So SQL has a built-in language it's a kind of a procedural language that complements the declarative language where you can run queries, that allows you to define functions in the same way you would do a function in Java or JavaScript or BASIC. I think it's actually very similar to some of the concepts in the BASIC language from many, many years ago. So the idea is, so you will be able to define functions in potentially different languages, like this SQL built-in dialect for sure, and then over time we'll add other dialects like JavaScript,
Python, and so on, or potentially leave the door open for plugin implementers to provide their own function language implementation. Then the next step after that is being able to support what's called polymorphic table functions. This is a different class of functions. It's functions that process tables and produce other tables. This is again one of those features that increases the power of the language dramatically. It allows you to do things you cannot do today. That feature we may actually interleave or do in parallel with the previous two things I was talking about. Eventually, we want users to be able to define their own polymorphic table functions and plugins to define their own polymorphic table functions at runtime as opposed to having to register them up front. And then finally, like this, one of the things that kind of builds on top of all these things I just talked about is the ability to run functions in a sandbox environment. Like if you think about, for example, the demo that Dana and David were given for Galaxy, and many people want to run Trino in hosted environments or managed environments like that. How do you allow users to provide custom function implementations? And you need to be able to sandbox that execution. So one of the things you have to protect against is bugs or exploits and so on. And in order to do that, you need to potentially be able to run functions in a more secure environment that is sandbox and unlimited from everyone else, any other execution, or even the engine itself. So these mechanisms that we're introducing in the function execution system will allow us to externalize the execution of functions and offload it to sandbox environment. And we expect this to be useful for many users, many companies that are running Trino in a managed environment in that fashion. All right, and there's a hodgepodge of other smaller features or bigger and smaller features that we're working on. There's a number of language improvements that we're tackling. We are in the process of getting, completing the implementation of Match Recognize. There's still one feature that's missing. It's support for aggregations in the context of Match Recognize, which again increases the power of that feature dramatically. So we're in the process of reviewing the code, and that will merge. It will get merged pretty soon. We've been working on support for merge for the last few months. Hopefully that will make it in. There's an open PR for that. And we're starting to look at support for some of the built-in JSON features in the SQL language. Trino supports a number of functions to process JSON. The SQL specification defines a set of built-in language features that make that set of operations even more powerful. So we're looking into that. We're going to be implementing and rolling that out over the next few months. And then we're also working on support for time travel queries. This is at least that's what we call them. The idea here is you can query the state of a table at some point in the past. And this piggybacks on some of the features of some connectors. Like for example, Iceberg has the ability to target queries over a snapshot of a table at any point in the history of the table. So we're adding the syntax in the engine and the ability to process that, and that will allow you to say, I want to run a query over a table on Iceberg, and I want to target the state of the table 4 months ago, and then combine it with other tables and so on. So that's also in progress. It's going to be in the engine pretty soon. And then we're continuing to do work on pushing down complex parts of the query, complex operations and expressions into connectors. There's some work that's going on to be able to push expressions, like for example, filters and function invocations into connectors. For connectors, I can take advantage of that. The canonical case here is if you have a query that is performing, a pattern matching over
strings, and you have a connector that understands how to evaluate those patterns efficiently, you want to push those down into the connector so you can take advantage of indexes or whatever other mechanism it supports. That's the first use case we're going to tackle, and there's a PR in progress to that. And then this is related to, I guess it's, so Trino is built on Java. Right now we're using Java 11, which is a few years old. And there's a number of improvements in Java 17 in the whole platform. There's new APIs. There's the vector APIs that allow us to target SIMD instructions in the CPU. There's language improvements that make the code base easier to maintain, easier to manage. And there are performance improvements. We've actually started doing some benchmarking with Java 17, and in some micro benchmark, we see like a 20% improvement in performance. So it is very important to be able to move to Java 17 as the platform on top of which Trino is built, and we're actually working on that. We hope to have that in place in the next couple months or so. And then finally, there are a number of connector improvements we're working on. For the Pinot connector, we're working on support for DDL, inserting data into tables, and a bunch of other optimizations. And in Iceberg, and the Iceberg connector, we're working on making getting the connector to be production ready, implementing a number of performance improvements, support for dynamic filtering, and other forms of pruning. And there are way too many improvements that people are working on to list in this slide. Okay, so that kind of covers the roadmap, and there's a lot of things going on. Like the roadmap is, as I said, it changes all the time based on what people are working on at a given point in time or willing to invest in. So you can always help if there's areas of the code that you'd like to get involved in. By all means, like we want people to help to contribute and help make that the implementation better and add more features. So there are a few resources you can use if you want to get involved in the project. There's of course the Slack channel. That's where all the discussions happen, discussions with developers, users having questions. If you need help, you can always find someone there. So please join us. And if you want to contribute code, there's a way. We have a couple of guides on how to get started doing that. There's a link here in the slide. And if you're new to the project and you just want to dip your toes and try to get a feel for how we do development, what the process is, there are issues on GitHub tagged with good first issue. Those are issues where we think they are easy tasks that are easy that are good for newcomers into the project. They are a good way to start learning about the code base and doing something that is very well scoped and limited in size, so you can get familiar with the project and the community. And then of course, like it always helps if you can try Trino. If you find issues, bugs, just report them. Let us know, and if you want to help fix them, that's even better. If you don't know how to write code, but you like writing, and if you're a user, if you have use cases you want to talk about, we have a community blog post, a community blog where we welcome people to contribute blog posts. You can just go to that link at the bottom, and there are, you can see all the previous posts, and you can get instructions how to contribute new entries. And finally, if you want to learn everything about Trino, we have the Trino book. There's a free copy you can get from Starburst. There's a weekly community, we call the community broadcast. This is like a video podcast type of thing, organized by Manfred and Ryan. And again, lots of very useful content. It's very technical. If you want to get into details about how things work inside Trino, if you want to know about Trino and the ecosystem, integrations with different connectors, different technologies. That's a really good resource. And if you want to join and participate in the broadcast, ping Manfred and Brian, and they'll get you on. Right? And with that, we're done. Thank you very much. Thanks for joining us.